So in a very short 7 minutes, I will just try to advertise my work. And even though it's not really related to BSM or any BGR physics, I will try to convince you that it can be actually very helpful to use neutron star as a tool for fundamental discoveries. So I will mainly focus on the equation state of neutron star. As already was mentioned by a very nice talk by Sanjay in the morning, what we theoretically know about the equation of states is low density calculation, which can be done within chiral effective field theory. What was not mentioned, we also have the perturbative QCD calculation at very high density that is start to be reliable at about 40 nuclear saturation density. That is far, far away from the density that can be reached in the course of neutron star. We also have a multiple astrophysical observation, and so what we can do, we can generate a bunch of different equation of states, condition all of them with your ab initio QCD and CET calculation and with your astrophysical data, and then start to study neutron star physics. So the majority of work that do something like that usually do not utilize perturbative QCD, understandably, because it's very far away. It's not even close to the course of neutron star. However, there are some amount of work that do that, and they saw the very big qualitative difference in the results. And so at this point, we came with my supervisor, Alexei Kurkela, and what we've done, we developed a new method how one can propagate QCD constraints from nuclear saturation density down to the neutron star density using just solely requirement that your equation of states should be stable, causal, and consistent. I will tell a little bit more about that on the next slide. For now, I just want to mention what we can conclude with that. It's just pure standard model and general relativity physics. I just find it very exciting, that's why I wanted to talk a little bit about that. So what we found, that the strong interacting matter inside the course of the most massive neutron star exhibit deconfinement behavior. We found that the posterior likelihood of having a quark matter core inside the neutron star is around 90%. And the remaining probability, about 10%, goes to the first order phase transition. I am very happy to talk about quark matter core, so if you have some questions, or just catch me after the talk. What I want to focus right now is how we can use this perturbative QCD input in order to test the underlying assumption. So we had two underlying assumptions here in order to claim quark matter cores inside the neutron star. It's a standard model and general relativity. So now let me tell a little bit more details about the method itself. So what we are doing, we have the PQCD calculation here, we have CET calculation here, and now we would like to connect these two limits somehow. So what we require, first of all, it's stable. Stability means that the second derivative of the ground canonical potential should be less than 0, therefore the function should be monotonic. It should be causal, that the speed of sound inside the neutron star cannot be bigger than speed of light. And it should be consistent. In this context, thermodynamically consistent means that we have to match 3 thermodynamic quantity in both limits. So this is pressure versus energy density. If you put just a line here between CT and PQCD, you will match pressure and energy density. But it's not enough. You also have to match a number density. Because if you just randomly put any line here, it's not necessarily will match the number density at PQCD limit. And so just these 3 requirements and your perturbative calculation can produce such a picture. And this red area all explicitly excluded by PQCD. And this is log-log plot. So for example, this red area at 5 nuclear saturation density is actually 75% of this black shape. So it's a big constraint. And the beauty of that there is no interpolation function. It can be done completely analytically. There is no model uncertainty, maybe except the missing higher order terms at the perturbative side. There is no astrophysical input whatsoever. It absolutely independent of general relativity. Therefore, it can be used in any alternative theory of gravity. So at this point, maybe I want to mention that if there is some ideas, I'm open for collaboration because we, for a long time, looking for test this thing beyond the general relativity. And so now switching to the standard model assumption, how we can test that neutron star actually made of QCD matter. So here we have a bunch of different observations, and the percent says how many equation of states are consistent with your particular observation. And so all of these observations, they come with different non-overlapped systematic and uncertainties. Therefore, a structure that encompasses all of this observation, all possible input that you can possibly have in your neutron star, is the structure that most likely to find the conflict between them. So for example, imagine that in the future, you will find some observation that will not overlap with the QCD circle. That it will indicate that there is something wrong with your initial assumption, mainly that neutron stars are made of QCD matter. So that's one of the ways to test the theory. Alternatively, what one can do, so what we are doing right now, we assume a standard model, have high density calculation, propagate it downwards, and then see how consistent it is with astrophysical observation. But one can also change the high density calculation. So if you have your Lagrangian and you can calculate something perturbatively, you can use absolutely the same method and the same thermodynamical relation to propagate your constraint down to lower density. Yes, so I think I will wrap here. Thank you very much.
We have time for a few questions.
Thanks for interesting talk. I'm curious if you match CFT and PQCD, not in the plane of pressure versus energy density, but in the plane of pressure versus chemical potential. Don't you respect thermodynamic consistency by construction in that case?
Pressure versus chemical potential. I think it's better. So the number density would be the derivative of pressure with respect to chemical potential, but then you will need to match the slope of the function exactly at PQCD limit.
So that's the only issue, right? But if you smoothly match it, then by construction you
but then
that, right?
define what you mean by smoothly match it. So I think it will not be that precise as what you can do, but yeah, it will be better than if you just use pressure versus energy density.
Okay, thank you.
There's a question back there.
Thank you for your talk, very interesting. I wanted to ask if your equation of state also include the information about the, sorry for my voice, because in modified gravity, often there are terms which include the higher derivative of the pressure or the energy density. So often, what happens often that you cannot use the equation of state you have in modified gravity. So my question is if from your procedure to obtain this equation of state, you have or you can get this kind of information, because it's quite crucial for modified gravity if you are interested in.
So what kind of information do you want to get?
Like, for example, high derivatives of the pressure and energy density, because you have those terms in the modified of equation.
So what we are doing is completely model agnostic way. So we have just generating a line using the Gaussian process regression. So I assume that then you have the full information and you can take any derivative you want.
Okay, that's great. Okay, so we can talk later. Thank you.
I don't see any more questions, but I do have a question. I think it's very interesting that you can derive useful constraints on densities that are relevant for neutron stars starting at very high density. I do have a concern about your conclusion relating to deconfined quark matter from observations. Do observations just suggest a softening of the equation of state, which is what I would assume, and there are multiple mechanisms in which you can soften the hadronic equation of state that doesn't involve deconfined quarks? So what is it that makes you think that this is a signature of deconfinement?
Yeah, that's a good question. So, of course, quark matter is a conformal matter, but not everything that is conformal matter is a quark matter. I completely agree with that point. So we looked at the multiple different observables, and one of them that makes us think that it's actually deconfined matter is the active degree of freedom, which in this case is just the ratio of P and Fermi-Dirac pressure. And as you can see, and you see that in multiple different observables, that you have this like nuclear band, and then you have a plateau all the way to PQCD. And so our active degree of freedom kind of tells that it should be some sort of deconfined matter. So it favors the interpretation of deconfined matter inside the neutron stars.
Okay, I think it's reasonable, but not watertight. Yeah. Any more questions? Yeah.
just out of curiosity, how robust are your results against the matching point of your setup? Because you choose like matching points, right?
Yeah.
So how much does it change? Or
So you're right that we are choosing the matching point where we want to propagate. And yeah, so the logic is as follows. You have your information on PQCD, and if you go all the way PQCD, you have 100% of the information from the PQCD side. If you start to push this construction down, you will lose information. And as far you push, the more information you lose. Therefore, we just decided to match it at 10 nuclear storation density because all of the equation of states collapsed already, so it's past the TOV point, but it's still not that far away from QCD, so that's just an optimal point that we choose. If you wanted to match it a little bit closer to TOV point, then you will lose a little bit of more information. So this is always the interplay, how you trust your interpolation function, for example. So you have to trust it as far as possible, then you will have the more information, basically.
So then in the data you provide, you already take into consideration these uncertainties on the matching point?
It's not an uncertainty in the matching point. So you just, if you match it at 5 nuclear storation density, you just have a smaller amount of information from PQCD, and that means that you assume that there are some crazy equation of states that can have like a huge phase transition and have speed of sound equal speed of light between your 5 and 10 nuclear storation density. But if you match it at 10, you'll just exclude it from your prior, because they are not consistent with QCD.